NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will build an intuitive understanding of how fractional exponents connect to radicals, prove the core rule, practice with a couple of clear examples, and then apply the idea to a real-world growth situation. Here is the key rule. For n greater than or equal to 2, a real number a, and any integer m, a to the power m over n equals the nth root of a to the m. If n is even, a must be non-negative for real results. Why is this true? Think of m over n as two steps. First, raise a to the m. Then, take the 1 over n power, which by definition is the nth root. Example 1. 2 to the 3/5 equals the 5th root of 2 cubed, which is the 5th root of 8. Example 2. Negative 125 to the 1/3 equals the cube root of negative 125, which is negative 5. Example. We will simplify a product that mixes negative and fractional exponents with radicals. Here is the expression we will simplify exactly as written, and then we will follow 4 clear steps. Step 1. Convert every radical into exponential form. We use the rule a to the power m over n equals the nth root of a to the m. Applying this to each radical term reveals exponents clearly. Step 2. Use negative exponent properties and simplify simple fractional exponents. 1 over a to the m equals a to the negative m. And the 5th root of 2 to the minus 20 is 2 to the minus 20 over 5. Hence, the second factor becomes 2 to the 4th, and the others stay as written. Step 3. All factors share the same base, 2. When multiplying like bases, we add exponents. Add negative 2.5 plus 4 plus 1.5 minus 1/2 minus 1/2. Step 4. Evaluate the power. 2 squared equals 4. That finalizes the simplification. We will solve an exponent product using strict step-by-step rules. Here is the example and the problem statement in orange. Step 1. Use the product of powers with the same base. A to the m times a to the n equals a to the m plus n. Combine all 4 factors into a single power of 3 by adding the exponents. Step 2. Add fractions by using a common denominator of 16. The sum is negative 15 over 16, so the exponent becomes negative 15/16. Step 3. Apply the negative exponent rule. A to the negative m equals 1 over a to the m. Rewrite the power of 3 with a positive exponent in the denominator. Step 4. Use the fractional exponent as a root. A to the m over n equals the nth root of a to the m. Convert 3 to the 15 over 16 into a 16th root. Final answer in green, 1 over the 16th root of 3 to the 15th. In this video, we will reproduce the exact step sequence shown, following the product of powers algorithm to simplify the expression. First, we display the example and the problem statement. Step 1. Rewrite the radicals as fractional exponents. The cube root becomes a to the power negative 2/3, and the 9th root becomes a to the power 2/9. Step 2. Use the product of powers with the same base. We keep the base a and add all exponents together. Step 3. Convert all fractions to a common denominator of 9 and then add them. Step 4. A negative exponent means reciprocal. So a to the power negative 15/9 equals 1 over a to the power 15/9. Step 5. A to the power 15/9 is the 9th root of a to the 15th. Step 6. Factor a to the 15th as a to the 9th times a to the 6th, so the 9th root splits into the product of roots. Step 7. The 9th into the product of roots. Step 7. The 9th root of a to the 9th is simply a. So the final simplified form is 1 over a times the 9th root of a to the 6th. Final answer, 1 divided by a times the 9th root of a to the 6th. Summary. We converted radicals to fractional exponents, added exponents for the same base, handled the negative exponent by taking a reciprocal, turned the fractional exponent into a root, factored inside the root, and simplified an exact root. Try a similar practice. Replace the 9th root with a 7th root and see what changes. We begin with the example and then carry out the algorithm exactly as written. Step 1. Convert every root into a fractional exponent using the rule nth root of x equals x to the power of 1 over n. We'll display the rule first. Now rewrite each radical. Step 2. When multiplying powers with the same base, we add the exponents. Let's show the rule. Now group like bases, a's together and b's together. Then add the exponents carefully. Step 3. A negative exponent means reciprocal. We show the rule. Apply it to both factors. Step 4. Convert the fractional exponents to radicals to present a clean final answer. The conversion rule again. Split a to the power 11 thirds into a cubed times the cube root of a squared. Substitute and simplify the denominator. Quick challenge. Try simplifying the expression b to the. We will simplify a power and root expression by following the exact step order shown. First, here is the example and the problem statement. Step 1. Convert every root into a fractional exponent. We rewrite fifth root of 4 as 2 to the power 2 fifths, fifth root of 2 to the negative 2 as 2 to the negative 2 fifths, and cube root of 2 to the negative 2 as 2 to the negative 2 thirds. Squaring that last cube root gives 2 to the negative 4 thirds. Now, everything is a power of 2. Step 2. When multiplying powers with the same base, we add the exponents. Add the 6 exponents carefully. Group fifths together and thirds together. That gives negative 2 fifths and negative 7 thirds. Converting to a common denominator of 15, the total is negative 41 over 15. Step 3. Convert the fractional power into a radical and handle the negative exponent by using a reciprocal. So 2 to the negative 41 over 15 equals 1 over 2 to the 41 over 15, which equals 1 over the 15th root of 2 to the 41. Step 4. Split the power inside the same root to pull perfect powers out. Write 2 to the 41 as 2 to the 30 times 2 to the 11. The 15th root of 2 to the 30 is 2 squared, which is 4. Therefore, our simplified result is 1 over 4 times the 15th root of 2 to the 11. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.